So that question never occurred. Yeah. I'll repeat it for the Zoom. So Ivan was asking, there's a choice of discrete torsion, and that comes in where there are many choices of choosing the Gauss law such that the product of all the Gauss laws gives you back the symmetry. So I was doing one particular one, but if you chose the other discrete torsion, you will get twisted gauge theory, divergence instead. Okay, so let me try again. I'll say the word condensation. Okay, it hasn't tried. So oftentimes you might hear people say, we condense. Condense the E anion. And what that does is turning on this sorry, I'm at the wrong Hamilton. Where is that one? We turn on this Z on each edge, right? And that is going to turn on, try to fluctuate or proliferate these E anions. So actually, one thing people are trying to say is that we shouldn't call this condense. Let's call this proliferate. Because you can always turn on some term to be strong. Doesn't need to be hopping a boson. It could be hopping a fermion, right? So you can proliferate the fermion, but the fermion won't condense, for example. So let's call it proliferation, for example. So that term is going to drive us to the confinement. But you might also hear when sometimes people say, we condense the E anion, and it takes you back to the paramagnet. That's also another group of people would say this. And you cannot tell the difference because at the end of the day, they're both trivial states. So correct answer. We got arrived at the correct answer 2 different ways. But notice that the symmetry is different. Right. Okay. So my claim is gauging is precise up to this discrete torsion, and it'll take you back to this paramagnet. So that's precise. So we should call this gauging. And when we say proliferate E anions, it means going this way. Okay. So similarly to proliferating E anions, if I'm in the Ising model, I can also turn on the Ising term to be strong, right? And what is this doing? The Ising model is creating a single Z, like it's now a charge, right? The physical charge of my zero form symmetry. So turning on this to be strong means I proliferate the charge. So proliferate these charge. And they look very similar because here, the E anion is a gauge charge, whereas here is a physical charge. And now to come back here, you could say, starting from the ferromagnet, I turn on this to be strong. What does X do? If I'm in the ferromagnet, right, it creates, if I have all my spins pointing up, right, and I act an X on a single spin, it's going to flip one of them to be down, right, and it's going to create a domain wall. So by turning X to be strong, you can say you proliferate the domain wall. Okay. And similarly, to come back here, there's an analog of this, right? Which is to, that corresponds to turning on that vertex term, right? Which is the kinetic term for the one form symmetry. So you could say it's proliferating one form domain walls. Here's a zero form domain wall. This is a one form domain wall. But now, okay, let me just pause here. Is there any questions about terminology? These are just definitions at this point, but now let's revisit why people call gauging. Oh, I'm sad. Let's revisit why people call this gauging a condensation. So let's see how we fix it. So let's visit this part here. So notice that when I said that, for example, I proliferate the E anion, I'm just basically turning this on I'm just turning this coupling to be strong, right? Z. But now let's look at what is the gauging doing instead. Suppose I start, oh, I'm pointing at the wrong place. I started with the Z2 gauge theory, right? And I turn on J to be strong. Yes, yeah. That's the proliferation of E anion. But notice when we do the gauging, what are we doing? After we introduce something, we turn something on to be strong. So what is this doing? So first, let's revisit this picture. So gauging the one form, so revisit it. Okay, so I started from this Hamiltonian, right? And then I introduce an auxiliary Hilbert space. We've called it the two-form gauge theory. But look, I initialize it as x equal to 1. What is the ground state of x equal to 1? It's the paramagnet. So I actually, what I'm in the 1 is equivalent to introduce a paramagnet with a zero form solution. Paramagnet, you can just think of a trivial state. I introduce an auxiliary state with a zero form symmetry, just sitting there, it doesn't do anything. And then I impose the Gauss law. So instead of imposing it as a constraint, let's do it energetically. So we add VE to the Hamiltonian, maybe let's say minus lambda, and then we tune lambda to infinity. Right. So this is condensing something or proliferating something. What are we proliferating? What is GE? Well, GE is made out of DZ on equilibriums, right? And so this is the local symmetry action with the two-form gauge theory, two-form gauge field sandwich side, right? But now, what is this in the Ising model? This thing is the Ising term, right? So we rethink of this as the Ising term. The Ising term has a charge, right? So dV is zero form V2 charge, right? So it's creating two of them. And then dE creates two E's at the endpoint. So what are we proliferating? We're proliferating, let me call this C. So on each edge, the term you're turning on is proliferating E, but also C at the same time. So condensing E takes you this way, but now I introduce a paramagnet of the Ising model, and then I proliferate E times C, right? After proliferation, this thing condenses. So in the condensate, E gets identified with C. So your gauge charge gets identified with the physical charge of this auxiliary system you introduce. Which is why afterwards, you end up with a trivial system, but it still remembers that it had a dual zero form symmetry because you introduce that implicitly, right? And the gauge charge gets identified with the physical charge. So you can think of gauging the one form as a proliferation, but not. So when people say, I condense the E and I go into the paramagnet, what they're secretly saying is I'm condensing E, but also bound to a physical Z2 charge. So that that is what they say. And then they say gauging is condensation. They're saying I'm condensing the anion, but I'm also tacking along a charge of the dual solution. So that's where the confusion comes from, because when they say that, they secretly don't tell you the full thing they have in mind. But this is what actually is happening. Reverse, gauging the zero form, you can also say, instead of condensing the domain wall, right? You're condensing the domain wall attached with the one form charge. So the one form charge is also a loop. Domain wall is also a loop. You condense them together, and that will take you back up here. And notice that I can do this either from here or from here. So I can do this regardless of whether I'm starting here or I'm starting here. I can always go up. Okay. Any questions?
Lattice, which is just proliferation for condensation.
Sorry?
Which is just use proliferation to condense instead of condensation because they ask
That's what people are advocating now, I think. But proliferation sometimes does condensation, sometimes it does not. As I mentioned, you can proliferate fermions.
That's right.
Okay. So okay, I have a few minutes left. So now let me tell you why I started with 2 plus 1D and not 1 plus 1D. Because if we drew the same thing in 1 plus 1D, I will have ferromagnet, and after you gauge, you can gauge a zero form, and then you'll get a dual zero form, which itself can have a phase diagram, which is ferromagnet and ferromagnet. But now with the couplings swapped, right? This is also J. So condensing the domain wall takes you that way. But you can also say condensing the domain wall with the dual charge takes you this way. In either case, you end up with a paramagnet. But because they give you the same answer and the symmetry looks the same, that's why you might be confused, because there are 2 distinct processes you can do. But that's why I start from 2D first, so that it looks different. But then now next time we're going to come back here and talk about how this can give is related to Kramers-Wanier. And Kramers-Wanier is going this way and then flipping the phase diagram.
Sorry, but here the global symmetries were different. So there is something you can say. But here are the 2 paramagnetic phases don't they have the same global symmetry?
Yes, yes.
So what's the difference?
It means that, for example, if there's a transition, right, it must happen in the middle. Whereas here, there's nothing you can say about the transition where it is. Was that answering your question? And the second thing is, even if we don't know where the transition is for some other model, we can still say that this point here will be invariant under gauging and some basis transformation, which we'll do next. So then that will lead us to Kramers-Wanier as a non-invertible symmetry on the lattice.
The common step is to line from couple one. Right?
Yeah, they're the same.
Yes.
They just
They're just swapped.
yeah. Whereas here they're not.
Yeah, so you cannot.
Yeah. Okay, so let's. We have 3 minutes for more questions. Everybody want to go enjoy Paris?
That's
Ready to go.